This is a demonstration video of a standalone Z80 computer system with a memory map display and a PS-2 keyboard interface. This is the main circuit board of the video system. This is the Z80 processor, an 8 kilobyte ROM, and 64 kilobytes of memory integrated circuits. This one has the video display memory in it. This is the video display output section with the voltage dividers and the output transistors. It's an 8 megahertz oscillator. There's a detailed explanation of the schematic of this circuit later on in this video. This is the PS-2 keyboard interface. I didn't have a proper socket, so I just wrapped wires around the pins of the keyboard plug. But the hardware is very simple, as you can see. This is an optional serial port used for loading programs into the system. It's not needed for console input and output as it is in the single board Z80 computer. Now I'll just run through quickly a demonstration of the standalone Z80 computer. So I've got it connected to this monitor. This is an old monitor from an Apple II system that I had a long time ago, and it works pretty well. So I powered on the computer, and here's a greeting message. Right now it's running the system monitor. It's very much similar to and is derived from the monitor for the single board Z80 computer, with some differences. So like the single board computer, if you type question mark, it'll tell you what commands are implemented. Dump is a command that displays memory. Load is a command that takes input from the keyboard in hexadecimal characters and puts it into memory at the address you specify. Jump and run do the same thing. They just jump to a particular spot in memory and execute whatever code is there. Question mark and help do the same thing. Using question mark just displays the commands. Bload is a binary load that takes data from the optional serial port and puts it into memory. Bdump does the opposite. It dumps binary data from the memory to the port. And finally, there is a basic command because this ROM has integer basic in the ROM. So just some demonstration. I'll just do a dump command so you can see how the display works. So I'll just dump what's in location 0, which is the start of the ROM, and that's the code that's inside the ROM. If I type basic, whoops, didn't spell it right. There we go. This starts tiny basic. So just to run a quick basic program, turn on caps lock. Whoop, don't like that. So that's a quick program just for incrementing a number. So we'll just run that. So you can see the basic program is running. And like the integer basic in ROMs for the single board computer, Control-Z will stop the program. I'm going to go through the schematic of the video display system quickly. Here is the Z80. That's used in this computer. This is a Z80B, which is rated for 6 megahertz. I am running it at 8 megahertz, overclocking it just using the dot clock oscillator, and it works well at that speed. A couple of differences in how this is connected in this system versus how the Z80 is connected in the single board computer system. I'm using a RC oscillator to give about 6 cycles per second signal that goes to the non-maskable interrupt. This provides a timer tick that's used to blink the cursor on the display and also to implement a delay to allow the keyboard to initialize when the computer's powered on. In addition, the wait input is occupied by a signal that comes from the video display to tell the Z80 to wait while the display is putting data onto the screen before it tries to write anything to the video display memory. So the data and address bus outputs are here and carry over to a memory area. So the computer has 8 kilobytes of ROM. The enlarged ROM, there was only 2 kilobytes in the single board computer. The 8 kilobytes is needed because 6 kilobytes is for the monitor and for the code to get keyboard input and to display characters on the screen. The extra 2 kilobytes in the ROM I use to I put the tiny basic interpreter in there. Then there are 64 kilobytes of RAM. This is hooked up in a regular fashion. This RAM IC contains the video display memory, which occupies 9600 bytes. The entire RAM can be used by the CPU, but 9600 bytes of the RAM is used for the display. The way the display is hooked up is through a large multiplexer. The multiplexer has 2 inputs. One input is the address bus from the CPU. The other input is an address obtained from a byte counter. So this counter cycles through 9600 bytes and is used to load the bytes from the display memory onto the screen through this shift register. When a byte is loaded into the shift register, the clock pulse, which is the dot clock running at 8 megahertz, shifts the byte through the register so that each bit of the byte is sent out over this output into the composite video output section, which is here. I'll talk about that in a minute. When the display is putting bytes into the shift register, the load byte signal is active, and it's just loading the bytes into the shift register every 8 clock ticks, and the shift register is outputting the bits one at a time, starting with the most significant bit of the byte first. Now, loading these bytes, the timing has to be exact, because when you load a byte, the most significant bit of the byte is immediately put onto the output. And that byte has to be loaded at exactly the right time. You want to load that byte right on top of the clock pulse. And so this is the circuitry for the load byte system. First of all, there's a divide by 8 circuit here, because the clock ticks coming in are at the dot clock speed, but you're only loading a byte every 8 dots. And you don't load it exactly on the 0 because you need to give some time for the memory to get the address and then put the byte on its output. So the load byte signal, I think, is put on count number 4 or something. The flip-flop just prevents any false edges coming from the counter, essentially makes it synchronous. Because you have to adjust the load byte signal to put the byte in the shift register at exactly the right moment, I use this delay with a adjustable trimmer capacitor. I then adjust this capacitor to give me a good picture using a test pattern where every other bit of the display is on, and I just adjust this capacitor to get the timing exactly right, and that seems to work well. Now, when the display is off, that's at the end of each line and at the space between the video display frames. The CPU can put data into this RAM through this bidirectional data bus buffer. When the load byte is not working, when the display is off, the bytes don't appear in the shift register. They only go into the RAM here. And similarly, when the display is off, when you're reading a byte, it doesn't appear on the display output. Bytes only appear when the load byte signal is on. So that's briefly how the display memory is attached to the system. Now let's look at how the sync pulses are generated and the display on-off signals are generated. The 8 megahertz clock is fed into a counter. This counter is for the dots across the line. The output of this counter is fed into a programmable logic IC that produces output pulses at certain counts to cause the display to do certain things. Similarly, when this counter is reset at the end of the line, that pulse will go to a line counter that again will cause the display to do certain things at certain line counts. These tables show how this process works. The counter is read by the logic in the programmable logic ICs, which put out pulses of 1 count duration on various output lines. So when the counter for the pixels across one line reaches 12, the logic will send a pulse out on the horizontal sync on output. When it reaches 49, it will send a pulse out on the horizontal sync off output, and the timing between these two is 4.7 microseconds, which results in a proper horizontal sync pulse. When the pixel count reaches 132, you have an output on the RAM2 off bus output. This takes the RAM2, which has the video display memory, off of the system bus and connects it to the byte counter through the multiplexer that we saw earlier. Then the display on pulse is set at pixel count 136. This starts the byte loader, which loads bytes from the video display memory into the shift register. And here at count 456, so after 320 counts, that's 320 dots, this stops the load byte signal, and then a few counts later takes the RAM and reconnects it to the system bus. Then at count 508, the counter is reset back to 0. This gives the proper timing for the entire line for composite display. Then the pixel counter reset is fed as the clock pulse into the frame logic, which counts lines going down the screen. So we take the RAM off bus at line 6. That's getting ready to display the pixels. And then we tell the display to turn on at line 7. So when both display on from the frame and display on from the line are on, then the load byte starts dumping bytes into the shift register. Then after 240 lines, the display is turned off. The next line, the RAM2, is reconnected to the CPU. And then a vertical sync pulse is sent that lasts 3 lines duration, and then the line counter is finally reset at 263 lines. So here you can see these outputs. So the horizontal sync on for the line is here, the horizontal sync off from each line is here. They act as set and reset for this flip-flop, which produces the horizontal sync pulse. Similarly, for the lines, the vertical sync pulse on signal here and vertical sync pulse off here is fed to this flip-flop. Vertical sync on sets it, vertical sync off resets it. This produces a vertical sync pulse. These two pulses are ORed together by this gate, and this produces a composite sync signal that goes to the video display output. And here are the display on pixel and display off pixel signals that result in the display on signal, which goes to the portion of the video display that loads bytes into the shift register. And then here are the RAM off from the pixel counter, RAM on from the pixel counter, RAM on from the line counter, RAM off from the line counter. These signals are combined and produce signals to tell the display to put the video display RAM on the bus, or to take the RAM off the bus. And then you have the reset output from the pixel counter that resets the pixel counter, of course, but also serves as the clock pulse for the line counter. And then finally the reset line counter pulse resets the line counter. And that's how the display is controlled. Let me just go through real quick the output system. So the video output is TTL level from 5 to 0 volts, but composite video wants to see something more like 1 to 3 volts for white and 0.2 volts for black and 0 volts for a sync pulse. So this voltage divider produces the video levels of about 1 volt for white, 0.2 volts for black, and the whole thing is pulled down to 0 by this transistor when a sync pulse is given. So one special thing to note here is this diode in the video display portion. This is a Baker clamp diode. I at first just had a straight transistor putting out the video, but I noticed that the dots were being smeared toward the right, and it turns out that this transistor will turn on very quickly. These are just general purpose bipolar NPN transistors. It turns on very sharply, but then it turns off rather slowly, and that smears the dots. And so looking around, I saw this Baker clamp idea, which allows this transistor to turn on sharply, but then to turn off sharply. What the diode does is as the transistor turns on, the diode feeds some of the current back through the collector, and this prevents the transistor from becoming overly saturated, so that when the transistor turns off, it's able to shed the charge very quickly, and this really sharpened up the dots on the screen a great deal. So that was an interesting thing I found out. You don't need this sharp turn-off for the sync pulse because it's not as sensitive as the video display dots to turning off quickly. So that's basically it, the overview of the video display. Now I'll go over the keyboard interface schematic. This interface connects a PS-2 style keyboard to the system. It is one way only, it gets data from the keyboard for the system. It's not capable of sending commands to the keyboard, so you won't be able to turn on the caps lock LED or change the key repeat frequency, but overall that's an acceptable trade-off. It keeps the hardware very simple. So the way the keyboard sends data is an 11-bit serial stream. The keyboard output, besides the plus 5 volts and ground, sends out a keyboard clock that is synchronous with the data pulses that come out on the data line. I feed the data into 2 serial to parallel shift registers hooked up in tandem to capture the whole 11 bits of keyboard data. That 11 bits, the first bit that comes out is a start bit, and then there are 8 bits of keyboard scan code data, followed by a parity bit and a stop bit. So the way I do this is I pull the keyboard port on port 5, which is this shift register, and look at D5 of that byte, and when a 1 appears in this bit, then I know that the full 11 bits of a key code of a keyboard data output has been received by the registers. And once that has been received, I read the data from both registers and use the CPU to extract the 8-bit key code data from that. After that's read, I reset the registers by sending an output to port 5 that clears both of the shift registers. This is just a little bit of logic to implement the port addresses, and these are connectors to connect it to the system, and I pass the signals over to another connector that connects to an optional serial port. So actually this keyboard interface is pretty simple. That's the end of this video. Thanks for watching. For more information, please visit cpuville.com.